All right, good. So we are here. Welcome, everybody. I'm Simon Peyton-Jones, and I'm thrilled to have you at this rather unusual conversation. So Arvind and Guy Steele are two giants of the functional programming community. Their influence has been profound, broad, and sustained over at least 5 decades. So I'm really pleased that they've agreed to have this informal conversation, which was going to be round a crackling fire in person with drinks, but alas, it's somewhat remote, about their journeys through the world of functional programming and their reflections about what has happened and what is yet to happen. So Guy was always planned to be virtual from the beginning. Arvind made a long and somewhat torturous journey here via Istanbul, and then on arriving has gone down with COVID. So I'm so sorry, Arvind. If you fall over sideways during this conversation, we will know what happened. Thank you for joining us virtually. So I think what I'm going to do is I'm going to engage in a kind of conversation with Guy and Arvind and get them to reflect a bit on their journeys, and then save up questions. I think we'll mostly have them at the end, unless there's anything super urgent. You can do that either in person, I'll try to leave some time, or by AirMeet, and John Reppy here is collecting AirMeet questions as we go. Does that sound all right? But I'm going to start off by taking us back to 1978. That was an important year. For me, anyway, that was the year in which John Hughes and I were in our final year at Cambridge. We had been studying maths. John, we both started studying maths. After 2 years, I decided it was just too difficult and went off to do electrical engineering. John, of course, cruised smoothly on to his maths degree. We both then did a postgraduate year in computing at Cambridge. But more importantly for this conversation, I think 1978 was the year you joined the faculty at MIT, Arvind. Jack Dennis hired you. And then you joined or maybe founded the MIT Dataflow Group, which we'll talk about quite a bit. I think that was the same year at which you, Guy, published Rabbit, a compiler for Scheme, whose cleverness I was still decoding, at least a decade later. And if those of you who haven't read that thesis, you would enjoy reading it, I think. It was also the year, or very close to the year, in which John Backus won the Turing Award. He won the Turing Award in 1977. You remember that was it's the sort of the Nobel Prize for Computer Science. And in 1978, he gave the Turing Award lecture, which is entitled, "Can Programming Be Liberated from the von Neumann Style?" A functional style and its algebra of programs. So that was kind of like, that was saying to all of us, look, have no truck with this dross of imperative programming by mutation. Functional programming is the future, and we shall design new computer systems to execute it. So that was pretty exciting. And for me as an undergraduate, and Guy and Arvind was somewhat more established at that stage. And 1978 was also, very close. 1979, I think, was the year that Mead and Conway published their book called Introduction to VLSI Systems, which was a kind of democratization of VLSI design and meant that VLSI design was moving out of the ambit of just if you were at Intel into at least universities. So I was wondering if we could start, maybe both of you, by telling us a bit about the journey that led you to 1978, what you were trying to accomplish at the time, and what programming language research felt like at that time. So maybe, as it were, go back a bit at a time and lead up to 1978-80 at MIT. Arvind, do you want to start with that?
Sure. I graduated, I finished my PhD in 74 and joined University of California at Irvine. And my PhD was all about, there is echo here. Can you guys hear it?
Yeah, but we can hear you enough. Enough? We can pause. Yeah.
All right.
Keep going.
Good. So I think my thesis was on modeling program behavior for operating systems, evaluation, and so on. And by the end of it, I was convinced that this was a bogus idea, because the models were just so wrong that anyway, the main decision I took at that point was I only want to be involved in the design of real things and evaluation of real things, as opposed to models of things that may be done. And at that time, I came across some papers by Jack Dennis on data flow for signal processing, and they profoundly influenced me. So I thought that was cool. And I said, I'm going to do parallel programming and languages, for the next 10 years of my life, which I did actually. And then I also came across John Backus's thing, and I don't know why I read his paper, but there was a paper in Popple 2 or something, on his reduction languages. And I pursued both of them, though I couldn't relate the two ideas together at all, what John was saying and what Jack was saying. But the most interesting thing for me personally was that uh, data flow graphs meant, I mean, what Jack was doing is that you had to draw these graphs. And I think I was kind of a world champion in this. I mean, I was drawing very, very big graphs. And by very big is all relative. I tried to do 8 queens problem in data flow as defined by Jack Dennis. And it filled, lots of space. And I said, this is no way to write programs. This is too verbose. And even if you were clever with visual tricks, it's not going to get there. I mean, I wanted to do a visual language. So that's how Irvine Data Flow Language, or ID, was born. And every construct in ID was designed so that it directly translated into data flow graphs. So compiler was not an issue for me. And this was also the time when structured programming was very big. So ID by definition had only, structured constructs, very few of them. So on the way to MIT, I happened to visit Tony Hoare at Oxford. And Tony said, okay, explain me, what is this ID language you're talking about? And I understood very quickly that he was least interested in data flow graphs. He just wanted to understand the properties of this parallel language. And I tried, and it was very clear to me that nothing was getting across. I mean, he was just kind of shaking his head and, disgusted or something. I don't know what. So at one point he said, stop, Arvind. Tell me, what is the purpose of a high-level language? And I confidently replied, to be expressive, right? He says, really? I mean, don't you think assembly language is expressive enough? I said, oops, where is this going? I thought about this problem. So I stuttered and, I kind of gave some very weak answers, which I didn't believe myself at that point. So he says, young man, the reason for designing a high-level language is to place constraints on our thinking without loss of generality, right? So we want to be able to say everything, but it should be constrained enough so that we can argue, algebraically or some proper semantics for it. And I tell you, that statement has such a profound impact on me that within a few months, 3-4 months after visiting Tony Hoare, the size of ID language has reduced by 50%, because 50% was just decoration. Nothing to do with anything real in it. So my advice is, please visit grand old men. Sometimes they do give you wonderful advice. I'll stop there, Simon.
So there you landed. So then you landed at MIT, and
that's right.
So this was the time at which you were first connecting data flow and lambda calculus, I think, because from what you were saying,
that's right.
Data flow initially was sort of a graphical thing, right? Nothing to do with lambda calculus.
I think what was very clear is that data flow, just like functional languages, had no side effects, right? So that was the intellectual closeness of the two things. But when you start with data flow graphs, and you start with pure lambda calculus, where you may write integers, the distance is very large, and it was very, very hard for me to connect the two, and that took a long time. And several people who played key role in this Zaina was one. She was equally interested in that topic, and Keshav Pingali and several others. And Joe Stoy was there. He was visiting us at MIT. So we used to struggle with these issues, and it was great fun to try to understand all this. And if I may just say one more thing, it was with the view of bringing these communities together, because data flow was already a pretty thriving community at that time. We used to have annual workshops and so on. We organized a workshop at Irvine where both Backus and Dennis were speakers. And then we organized this functional programming languages in computer architecture, and I was able to find the. Can you see this?
Yes, yes.
Right.
FPCA,
So
Functional
this was
Programming Languages Computer Architecture,
1981.
which a conference you started, right?
Right. And within about after about 5, 6 meetings of that conference, it was alternating with the LISP conference at that time. It was clear that people from architecture community were not going to submit papers to this conference,
Yeah,
so
we're
it
going to
did
come
not
back
make sense.
to
Oh,
FPCA.
okay, sorry.
We're going to
Good.
come back to that. Let's talk to Guy a bit. So Guy, around the same time, I think you described yourself as sort of hanging around at MIT in the
Yes.
late 70s, early 80s. Is that right?
Yes. So my journey to 1978, that comes in two parts. But it started when I was 14. I was a student at the Boston Latin School, and unusually that school had an IBM 1130 available for its students to use. And shortly after getting involved with that, I got involved with the MIT High School Studies program. MIT had many courses that MIT students would teach to high school students. This gave me access to computers at MIT as well. And I learned that if you were well behaved and didn't cause any trouble, you could just walk into the document room at Technology Square and get artificial intelligence memos. And so I helped myself to various memos there, and I was an avid reader. And some of these were about how Lisp worked. Through those connections, I also learned about the MIT Press book sale, and for cheap, on my limited budget, I was able to buy some artificial intelligence books by Marvin Minsky, and also a copy of the Lisp 1.5 Programmer's Manual. Also, there were no locks on the doors. I could just walk in and use the main computers at the AI lab. Again, as long as I kind of stayed out of the way. So I was able to use MacLisp and compare it with what I was reading in the manuals. And by about 1971, I thought, this is interesting. I'm going to try implementing a Lisp for myself for the IBM 1130. So I did that as a project. I was probably 16 then. And so by the time I graduated and was ready to go to college, I had a pretty good working knowledge of Lisp, and I'd implemented one. And my parents said, okay, now you need a summer job, between high school and college. So I applied to a couple of local firms to work as a key punch operator. I figured that was a skill I had. I knew how to punch cards. But they wouldn't hire me because I wasn't 18 yet. But then I heard that Professor William Martin at MIT was interested in hiring Lisp programmers. So I walked into his office, bold as brass, and said, I heard you're looking for Lisp programmers. And he kind of looks me up and down and says, okay, you have to take my Lisp quiz. And I took his Lisp quiz and passed. So he hired me on the spot. And so I became the maintainer of MacLisp for the next 8 years, the MacLisp interpreter, while John L. White took over the compiler duties. He had formerly been doing both. So that's how I got a job at MIT, and I held that job for 8 years, all while I was in school. It was part-time during the school year. So that's how I got into Lisp, in short. And about the time I became a graduate student, I was looking for an advisor, found Jerry Sussman, whom I already knew because I'd been with the AI lab for a few years, serving as a maintenance programmer for MacLisp. And we were interested in Carl Hewitt's theory of actors, which was kind of what we now call very object-oriented. And we wanted to understand how this very complicated language of his worked. So we decided to build a simulator, a small simulator. And we implemented that simulator in Lisp because Lisp was a good rapid prototyping language. And so we implemented some of the actor features, and we built it on the substrate of something like Algo 16 because Sussman had been teaching Algo 16, of course, and thought that the lexical scoping features of Algo would help us to better reflect actors' need to keep track of acquaintances. So we did that, and we ended up building like a small list that was lexically scoped with actor features added in, and we found that we could apply lambdas and it behaved like lambda calculus, and we could send messages to actors and they would react, and we were very happy with this. And we also experimented with other things such as whether it should be called by name or called by value, and experimented with various efficiency tricks for keeping track of environments. But one day, while inspecting the code of our interpreter, we suddenly had the realization that the code that implemented lambdas and the code that implemented actors was identical. And we didn't understand why, because we thought of them as having very different behavior. But we decided, well, if they have identical implementations, then they must have identical behavior. And we soon, well, not so soon, but after struggling through it, realized that the differences in their behavior had to do with the primitives we were using, and not with the essential nature of an actor or a lambda. So we were using actors to invoke actor-like primitives. We were using the lambdas to invoke functional primitives. And that's why we were seeing a difference in behavior. But the difference was an illusion. And so that was the invention of Scheme. For my master's thesis, I decided to build a compiler, the Rabbit compiler to which you alluded. I did most of that work in 1976 and 1977. And that brings me up to 1978. So that's what I was doing before then.
And your collaboration with Jerry Sussman went on to produce this amazing sequence of papers, the Lambda, the Ultimate papers, which if everybody here hasn't read them, you should go and read them. They were a source of inspiration to me, and I just wondered how did they come about, that particular sequence? Because they weren't published conference papers; they were kind of MIT AI memos, weren't they?
Yes, we were just busy with the excitement of discovery, and we wrote things down and tossed them into the memo bin as quickly as we could. We were less interested in conference publication than just finding out what's going on here. So now that we'd managed to explain actors, we realized that, well, lambda expressions seem to be pretty powerful. We were aware there was a literature, so we started reading the literature, including some of Joe Stoy's work on denotational semantics, and realized there was already this work available that explained how a lot of programming languages worked in terms of lambda calculus. We had, in effect, built a practical interpreter for lambda calculus. So we merely transcribed all of those lambda expressions into parenthesis syntax, and to our happiness, we're able to run all this stuff directly. And so we got into, in effect, bringing denotational semantics to the masses by recoding them into an actual working practical programming language, and then wrote this down in memos. We kind of feel like we hadn't invented anything new. We're kind of transcribing it into a working engineer's notation. And so with Lambda, the ultimate imperative, we were trying to explain all the imperative constructs in languages. And with Lambda, the ultimate imperative, we were trying to understand binding and how that worked. And we wrote a number of other papers from there. We were just trying to explain to ourselves all the things about how programming languages worked. And the discovery that lambda calculus is so powerful by accident, because we started with actors, was tremendously liberating intellectually. It kind of opened up whole fields of literature for us to exploit, so to speak.
I really like the way that you sort of somehow shared that joy in a very immediate way by writing an AI memo quickly, not waiting for a conference publication, just slammed it out. And you did that sort of successively for a sequence of papers. I found it personally very helpful to me, and I'm sure other people here have. Wave if you've read some of these Lambda, the Ultimate papers. Yeah, there you go. There's a lot of waving going on. Shall we shift gears a bit and talk about, Arvind, you mentioned FPCA, Functional Programming and Computer Architecture, and part of John Bacchus's Turing Award lecture was indeed about, it carried the sort of at least subtext of, maybe we should, in liberating programming from the von Neumann style, maybe we should liberate program execution from the von Neumann architecture, and we could build radically different machines, or maybe data flow machines, or SK combinator machines, who knows, to execute these things. And that would transform computer architecture as well. And there was quite a bit was going on at that time. You started the conference, right? I think Jerry Sussman implemented this chip, didn't he? Which you maybe had something to do with, Guy, that there was Lisp on a chip. Some friends of mine at Cambridge implemented in microcode a machine for executing SK combinators directly in microcode. So it had no other machine code. Its machine code was SK combinators. So there was kind of a lot going on, and we thought we're going to change the world. But in the end, the world kind of, and of course, very significantly, as you put in our correspondence before this, Arvind, you say you were consumed during the 80s with the task of building Monsoon, which was, the world's first physical embodiment of a large-scale dynamic data flow machine. They want to tell us something about that. But I'd be interested both in your feelings about what you were doing at the time and what you were trying to do and hoping to achieve, but also why in the end we didn't end up, FPCA isn't a conference anymore, and why I think our aspirations to influence the world of hardware have changed quite a bit. So Arvind, why don't you start on that, anywhere in that general territory?
So, it's hard to build any big piece of hardware, and Monsoon was a gigantic piece of hardware. It was a 16-node machine, but it was built from scratch. I wasn't using any microprocessors to emulate. Its architecture reflected what a data flow machine would actually be. And I think the reason why the project was exhausting and very big was because we had to do everything, all the hardware, all the software. And one lesson I learned from that was there is some I call visible software, right? So if you have to build a compiler for it, everybody understands. If you have to build some sort of an operating system or a resource manager for the language, everybody understands that. People even understand that you have to build, some sort of a simulator, for the machine, because you have to test out ideas. But in spite of all these, high-level things, the amount of invisible software involved in building the machine would outdo it by a factor of 2, right? So people are just slogging, always coding, right? And then you will, because for example, debugging Monsoon. We had no idea at that time. We were so naive that you need a proper test plan for it. Then to prepare a test plan and then to actually implement it. And then somebody comes and tells me, you realize that on Monsoon, 200 by 200 matrix multiply gives the right answer, but 400 by 400 matrix multiply doesn't.
Oops.
So this was like outside. I didn't even know where to begin debugging this thing because we had simulated everything. And it turned out that it was causing some congestion in the queue. And according to us, we were within the specs of the 54Q chips that we had bought, but apparently we were outside it or something. Who knows what? But it took like 2 months of debugging, to figure that out. There is nothing much to tell about that except like this, or during a cocktail hour, you can say, these are my stories, the thing. But I think the main reason why these ideas didn't go very far then, because I think they may still see light of the day, is because the progress of microprocessor in terms of performance was so dramatic that really none of us expected it. So parallel machines kind of lost their raison d'etre, because you produce a 4-processor machine and the next microprocessor is almost there already, right? So people were not interested in these parallel machines in terms of actual performance. And that's the reason why almost all the startups in this space died. Right? And situation remained like that. It was a little bit disappointing for us, but we understood it technically, what was going on. And it's only in early 2000s when finally big companies changed their rhetoric. First, they want to number of cores in the machine. But just to tell you, the difference was often an order of magnitude. My clock speed was 10 megahertz, while Intel was already talking of building a microprocessor that would run at, 80 megahertz or something like that. So how can you compete? So I think from users' perspective, parallel machines lost their thing. But one of the fascinating things for me is many things we did in 80s, people come and ask me, even today that, do you know about this thing? And because people keep rediscovering, as things are getting more and more parallel.
Every superscalar microprocessor is a data flow machine with register renaming and dynamic scheduling, isn't there?
So I couldn't hear you, Simon. Say it again.
Just saying that inside every superscalar microprocessor is a data flow
yes.
machine with a token store and dynamic matching and
Absolutely.
scheduling, all kinds of things that happen in Monsoon.
Right. And I think it's also happening now at the software level. I mean, when people are exploiting more and more fine-grained parallelism in their software, right? Many ideas are being borrowed from there. And then people start talking about, is there any hardware support we can provide for these more fine-grained parallel activities?
Guy, what in this general territory of functional programming and computer architecture, particularly in the sort of 80s and 90s?
Yeah, I'd like to jump in and say that I'm fascinated by the fact that we did have so much innovative hardware being designed in the 1970s and 80s. Monsoon is an excellent example of that, perhaps one of the more successful. But there were things like Lisp machines going on. Eventually, there were the large parallel machine companies in the 80s and 90s. I belonged to one of those, Thinking Machines Corporation. And some of the ideas developed in Monsoon and the id language influenced my thinking when I was working at Thinking Machines in those days. As did Bacchus's Turing lecture. So all these threads were kind of coming together and weaving together in different ways. But I think Arvind is right. It was very hard for the data flow machines and the Lisp machines and the scheme chips and the combinator machines to compete with Moore's law. And if all that stuff were happening today, it might be a different story. Now that we've mostly run out of Moore's law, we aren't seeing the clock speeds accelerate. The numbers of transistors on chip are still growing slightly. We're mostly using it to make parallel copies of stuff. So it was an exciting time, but as I say, we couldn't keep up. We mentioned the Mead and Conway book too, happening in 1978. I was a student in the course that Lynn Conway taught at MIT in spring of '78. And my student project was the first scheme chip. And by scheme chip, we meant a chip that would implement the list structure in memory directly. And for technical reasons, my student project failed. There was a design error. But the later Scheme 79 chip and 81 chips that Sussman and Jack Holloway and Alan Bell and others helped design did work and worked at a very reasonable speed, but still couldn't keep up with Moore's law. Not only couldn't keep up with Moore's law, but in fact, implementing list structure directly is really not a great way to implement scheme. It was really more of a demonstration that you could do that. And you're much better off letting a compiler jump in and make the optimizations first and compile it into something better, either a standard architecture or perhaps data flow.
It's not just Moore's law. It was what we learned in the 80s was that it's silly to build hardware to interpret stuff which you can instead do static analysis of and compile into instruction streams. So rather than interpret something at runtime in hardware, just do the work statically instead. That's why an SK combinator machine I now regard as being somewhat misconceived. Then we can ride Moore's law instead of trying to compete with it. But I was wondering.
The other thing I learned from Moore's law is that if my machine isn't quite powerful enough to solve a problem, instead of beating my head against the wall, I should just wait 3 years, buy a faster computer, and then solve the problem. And I actually did that to some good effect. I did that a couple of times during my career, and I told my son, who is now a computer programmer, I was able to benefit from that trick. You won't be able to. And it's too bad.
So true.
Do you think there are any, so although I don't think we're going to radically change the face of computer architecture, I still wonder if there are things that we could, somehow we could tweak existing architectures to be better for functional programming in ways that might be better for other languages as well. In other words, I don't feel as if the hardware road has quite run out yet. I wonder, are there any things that you wish were in, when you're building a compiler, that you wish were in the microprocessor you were compiling for? I mean, things like, I don't know, faster read barriers for garbage collectors or tag bits or something. Or do you think that that day is over? I guess either of you.
This question is for me or for Guy? Guy, you want to go
either
first?
of you. Yeah, I'm sure you both have opinions.
Yeah, some help for storage allocators is always welcome and helpful, but typically doesn't buy you more than factors of 1.5 or 2. And the garbage collector algorithms are continuing to evolve anyway, so it's really still not clear what to standardize on after 5 decades. The other thing is that some of the Lisp-like languages, at least, tend to be polymorphic in nature. And support for polymorphic arithmetic could buy you a fair amount of performance. And for example, the Spark processor architecture had some support for looking at the low 2 bits of a pointer to see whether it's really an encoded integer. The idea simply being to relieve the storage allocator of the load of allocating lots of tiny integers and instead just encoding them in pointers. So little tricks like that might buy you factors of 20% or 50%, or maybe even a factor of 2 in a really arithmetic intensive computation. But it's not clear it's worth completely contorting the architecture to make all that happen.
Simon, I don't believe that in general purpose architectures, any very specific support for a programming language is going to buy you much. Again, for the reasons you are giving, that compiling technology advances very rapidly too, and algorithms change constantly. So, but I think many of these tricks do find some place in hardware accelerators. So if you're designing a piece of hardware for accelerating something, then you do all kinds of strange arithmetic, right? You may want to do Galois arithmetic and so on because it's directly being used, in that. But the moment you start asking this question in a general purpose setting, it's very, very hard because number of jobs that actually use that stuff is so small that it's very hard to justify, and nobody can keep up with the speed of, designs of the commercial microprocessors just because of the effort that goes in.
Okay. Let's move on. I wanted to spend just a few minutes on sort of what happened next for you, Arvind, and then come back to you, Guy, about other programming languages. So, Arvind, you sort of moved on from Dataflow, founded Sunburst, and sort of pivoted entirely to work on Bluespec and hardware design and verification. Do you want to say a little bit about how, what caused you to do that pivot, and how rewarding you found it, and why you ended up doing that?
I think that's a very interesting question. The way I like to describe it is that until 2000, I was primarily interested in what is the best parallel programming language, because we were designing these hardware machines, and of course we want your programming language to be portable and so on. But after 2000, my objective became exactly the opposite. I was trying to see what is the best way of designing hardware. And hardware is all about parallelism, right? In hardware, you never think in terms of one thing happening at a time. So, and I also knew in some sense that the data flow model is inadequate because there are lots and lots of, at least at the specification level, and even at the design level, there are lots of things which you don't want to specify. I'll give you a very simple example. In speculative processors, you don't care after how many speculations the processor starts doing the right thing, right? That's a non-deterministic thing, depends on many, many factors inside the machine. So I knew that I needed a parallel language which dealt with non-determinism in a very friendly and good way, right? A desirable non-determinism of the things. And I started applying the things I had learned in describing programming languages, right? Like operational semantics. You give rewrite rules for various constructs. So what happened was that I've taught graduate architecture subject at MIT for about 25 years, and by mid-90s, it was very clear that these speculative processors are very, very hard to describe precisely. Same thing was true for cache coherence protocols. So, when your audience is smart, somebody says, well, what if I do it like this, right? And you say, sometimes it was clear to me that won't work. And sometimes I said, the idea is very clever, but I don't know what it does to the answers, right? Is it still correct? So that's how I got into it. So describe hardware very precisely using term rewriting systems. And that went on for 3-4 years. And we were convinced that we can describe anything, regardless of how complex a digital hardware you gave me. But then I went and gave talks at IBM and Intel and so on. My friends took me aside and said, why are you doing this? Right? Who cares about this that you have described precisely? I said, well, then you can decide whether it's right or wrong. He says, Arvind, we are not into theory. We like to design fast things, so leave us alone. So I was really going through a crisis trying to decide what is the next thing I want to do. And until we were having lunch, my students and I, which we often do, and one of them said, why can't we go the other way? I mean, if you can describe these hardwares so precisely, suppose I gave you this description and didn't show you the hardware. Why can't you generate it? And at the lunch table, everybody looked at each other and it says, why not? And that's what consumed us then. And then we went to synthesis, how to constrain the high-level description so that we can actually generate hardware. And that's how Bluespec was born. And some people played very, very key role in that, Lennart being the most important one. Lennart Augustin, I still remember sitting under the Eiffel Tower after one of the ICFP meetings there and explaining him how you could compile hardware from TRSs. And he said, makes sense. So that's how the company was born, Sandburst, and later on Bluespec. And that's what I still do.
Yeah. That has been a big shift. So the last 2 decades, this is what you've been doing, designing and verifying hardware.
Yeah. And Arvind has put us, I'd like to emphasize that Arvind is talking about a very, very important idea in the last several decades, which is that you're often better off, rather than designing something complicated directly, writing a program to design it or writing a program that describes it. And of course, his work with Bluespec, things like Verilog, essentially no complicated hardware is designed anymore without writing a program first, in effect. Even though the hardware designers will deny being programmers, that's what they're doing. No, I've had them deny it to my face, and I said, no, Verilog is a programming language. This is what you're doing.
That's right. Well, that's what programming language people do, don't they?
Just as a comment,
we say to people, what you're doing is really programming. I say that to Excel people. You're really just programming. They laugh.
At Sandburst, what I discovered was the difference between outstanding hardware designers and ordinary hardware designers was their understanding of programming languages. I mean, outstanding hardware designers have a very good understanding of programming languages. I mean, they just have to use them, right? And more languages they learn, better off they are. So people who say that programming language, I don't do programming languages, I do hardware, they're kidding themselves. In future, it's all programming.
Let me shift back to you for a sec. So there's quite a lot of people have played a leading role in one programming language. Like Bjarne Strostrup for C++ or Larry Wall for Perl and so forth. With many languages, there's one or two individuals you can explicitly associate. But I don't know anybody who has played a truly leading role in as many languages as Guy. There's Scheme, there's Common Lisp, High Performance Fortran, Fortress, and Java. And and these are not just, dabbled in them. You played a significant role in their design and implementation. So I'm interested in how that, a bit about how that journey came about. Maybe people here probably don't know as much about Fortress as they know about some of these other languages. So just interested in you, if you've got any reflections, Guy, on that sort of multi-language journey that you've done and how you ended up being so influential in so many languages. I'm quite curious.
I think it's because I just cheerfully volunteered to do the scut work that nobody else wanted to do. In particular, I enjoy writing, and I enjoy writing language specifications. And so when some committee said, okay, let's design a language, okay, who's going to write it down? I said, I'll write it down, and the project editor gets some influence.
Right.
So I've actually haven't initiated that many language designs. So I found existing projects where I felt I could make a contribution. And, I didn't design Lisp, but I helped implement MacLisp in extended a lot of ways. I wasn't the principal on any of the implementations that went into Common Lisp, but I volunteered to write the book, and to run the committee and stuff like that. So If you volunteer, you get a chance to do some work. That's really what it is. And I was fortunate to have a lot of opportunities, more than I expected to have to do that. Fortress is an interesting case where I was asked to lead a language design as part of a much larger project for Sun Microsystems as a part of the DARPA High Productivity Computing Systems project. And that was a hardware and programming language and operating system design. And we came up with I think, really a grand plan, but it was one of those competitive procurement things, and Sun ended up being number 3 on a list that included Cray and IBM. So we got 2 rounds of funding, did not get the 3rd round. So Fortress was developed to a certain extent. I think it's an interesting design, perhaps was too ambitious. So we learned a lot from it, but I think it was, in a way, too destined to fail. It had a 20% chance of succeeding. As I said, it had some ambitious aspects. There are 3 or 4 things that I could point to in Fortress that I think have influenced other language designs. For example, the way it does a conditional test and a conditional binding and an if statement has been adopted by Swift, I think. And I still think that Fortress's approach to operator precedence is superior, which is not to assign every operator a number and then compare the numbers, but rather to have a precedence graph. And the rule is, if you didn't learn the precedence rule in high school, you shouldn't use it in a programming language. Classic example of that is plus has higher precedence than greater than. Greater than has higher precedence than and or. But you don't want plus to have higher precedence than and or. That's just confusing. No point to allowing that.
Tell us a bit about the background to your talk, Growing a Language, which was, I don't know if any, wave if you've heard this talk or read it. So it's a sort of probably a minority of waving, but it's quite a tour de force. And I'm sure it didn't just, you didn't just think one night, oh, that would be a cool idea and produce it in the morning. How did it come about? And just
that talk took several months to write.
What was special about it? Why am I making a big deal about this particular talk, Guy?
I was asked to give a keynote talk at UPSLA in 1998. So I was asked, probably close to a year ahead. So Java had been out for a couple of years, and I was reflecting on how Java had progressed so far and the arguments we had had about the directions Java should take in the future. And so I got this idea that I want to talk about the evolution of programming languages. And I was thinking about the fact that other languages I'd worked on, such as Common Lisp, had grown over time. And I was trying to think about guiding principles for that design and how do you keep it from just being this large hodgepodge of unrelated features. And I had some ideas for topics, but really wasn't quite sure how to structure the talk. And I'd written a draft, and it was really kind of boring reading. And my colleague, Dick Gabriel, who is, by the way, a professional poet as well as a programmer, challenged me to come up with some artificial constraint. And this actually interestingly reminds me of Arvind's anecdote about Tony Hoare, saying you need this artificial constraint to guide your thinking. So he said, come up with some kind of artificial constraint and live with it. That's what poets do, write it as sonnets or something like that. And I thought, well, suppose I confine myself, the language of the talk itself, to some small subset of English. And I tried standard English, and that didn't work because it still sounded too Latin. There are too many words from Latin in it. So I cast about again and said, okay, I'm going to confine myself to words of one syllable as an arbitrary constraint and see what happens. And I discovered that the experience of trying to write the talk using only words of one syllable actually guided my thinking about the content of the talk in unexpected ways. And so the form and the content of the talk grew together, and it was really a surprising one-off experience. And I don't think I'll ever replicate that experience again. And I came that close to writing a compiler for the dialect of English that I was using to make sure that things were defined before they were used. But I've decided I didn't have time to write that compiler before I had to do the talk. So I just ended up eyeball checking it. I think I caught all the mistakes barely in time. But so the rule for the talk
2
was
syllables.
I couldn't. Yeah, that's right. I couldn't use any words of more than one syllable unless I defined the first in the talk. And so writing the talk felt very much like writing a program.
Yeah, and you allowed yourself to use
more than that.
words, but only when you defined them using one-syllable words. That was your
go. Realize that what a programmer is doing as he writes new methods, new procedures, is that in effect he is creating a new language in which he can then write further code and eventually the end application.
Yeah.
So that is a thought that I think I've seen quoted a lot on Twitter. You know, a programmer just doesn't write procedures; he defines a new language in which to go further.
So yeah, we're at 10 minutes. I'm on it. So in fact, I think we're going to sort of move towards wrapping up. So for Guy and Arvind, I was going to ask you something about what the future holds, right? So when I talk about functional programming, I often say, when the limestone of imperative programming has worn away, the granite of functional programming will be revealed underneath. But I think
Simon, if I may, I'd like to jump in and ask for 90 seconds.
Yes,
there's one topic I would like to address that is in our notes. One time, 8 or 10 years ago, I asked you, knowing now what you knew then, if you'd known then what you know now, could Haskell have been call by value rather than call by name? And you gave me a very interesting answer. Do you recall that answer?
I probably said, I'd have probably made it call by value, but then 5 years after that, I'd have said, oh, I wish I'd made it call by need.
My memory is what you told me is that, yes, all the stuff about monads and all the other stuff could have been done in a call by language, but you would have been tempted to put side effects into language and that would have destroyed the whole project. Call by name kept you honest about being pure and functional. And I thought that was a very interesting insight. I'd like to interject that Sussman and I looked at making scheme call by name or call by need rather than call by value. But our project definition was to try to encompass explaining all the programming languages, including the side effects. And we discovered that if we tried to use call by name, we couldn't understand what was going on with the side effects. And so I think I see a linear arc where with Scheme, we provided a piece of engineering that was call by value, allowed you to use the side effects and explain a lot about programming languages. And for a time, Scheme was also used as a basis for functional programming. But once Haskell appeared, that took over. And Scheme kind of decreased in the functional programming language, and Haskell became the language of choice for those further explorations. And I feel very satisfied with that arc of history.
Is much more purity is much more important than laziness.
Yes, the purity is the important thing.
Purity.
So Scheme played a role in bringing functional programming about, but it's also very good that Haskell took over when it did.
Is there anybody who wants to ask Guy or Arvind anything? Just sort of wave your arms, and somebody with a microphone go near. And meanwhile, I'm just going to ask Arvind if there's anything else you want to say about, what you think the future of functional programming might be, or anything that's come up here that you haven't had a chance to say. But meanwhile, in parallel, wave arms.
Well, one thing I just wanted to say is I have been wrong about lots of things in my life, but one thing I deeply believed was in 80s that parallel programming would be the normal programming and sequential programming will be taught as a special case of parallel programming. I mean, I really thought this will happen at MIT. To freshmen, we'll teach parallel programming. And 40 years later, this is just wrong. I mean, sequential programming remains very important. And I think people will have to master sequential languages. They just have to understand something about independence and lack of dependencies between things, that things can be done in any order, right? But that's a separate concern. And by and large, people do not worry about performance, just as most programmers don't, just as, we expect, well, Intel will give me a faster machine next year. So they expect compilers and all the basic software will just improve and, they have nothing to do with it. So parallel programming in that sense has fallen behind advances in concurrency and so on, which is also very, very tough. So.
Okay, there's a question here. So I hope you can hear this. Yell if you can't. Yeah, go.
So 13 years ago, Guy Steele gave a keynote at the ICFP.
Hang on just a sec. Can you both hear this?
Yes.
Yeah.
Yes, good. Okay, carry on.
Okay. 2009, ICFP at Edinburgh. I believe Guy Steele gave a keynote on fold considered harmful. So My question is just whether Guy Steele still considers full is harmful.
I do, and for exactly the reasons that Arvind just enunciated, which is that the ability to express parallelism and independence in computation is important. The particular definition of fold imposes a sequential composition on the functional program you write. And a very slightly looser thing, namely reduce, enables the parallelism and the independence of computation that allows the efficiency that Arvind talked about.
You mean you want a sort of an associative operator so that you can do it in parallel? Is that what you mean?
Yes, precisely.
Anyone else? I'm looking at. Can microphone people? Can you run to the spot? Thank you. Swiftly. As our precious seconds are running out. Run. This is Ron Garcia, by the way.
Hello.
I think.
Thank you very much for this conversation. I guess I have two questions, but I'll do one. To Guy Steele, as Simon was mentioning, you're one of the rare people who've been on many standards committees for programming languages. And I was wondering if you had any insights on what makes a standards committee or standards process successful or not. What kinds of properties of the people and the process?
While Guy's responding, if somebody else can wave an arm and a microphone can go, please. Thanks. Guy.
I think a lot depends on whether the committee is working towards some kind of common understanding and common good. Sometimes individuals will want to make their mark on a language, and that can kind of bog down the process. On the other hand, sometimes they have good individual contributions to make. I don't have any wonderful insight on what kinds of committees work better than others. Every successful committee, I think, has had one person who either strongly guides it or volunteers to do a lot of the work. I played that role in some cases. In other cases, you've got a strong personality, such as a Guido Rossum or a Bjarne Stroustrup, who kind of, leads the way and also does a lot of the work.
And as Simon has played in Haskell. No, really,
Yes,
I mean, I think more than the committee, it's the leader who can guide everybody, who can reach consensus as well as lead. I think that's what is essential for success of a good definition.
Yes, Simon is an excellent example. I also mentioned Rich Hickey's leadership of Clojure.
When, in the early days of the Haskell committee, we had a chair of the committee, but we also had a syntax czar, whose job it was we all agreed that syntax wasn't important, except that it was the thing that we really felt passionately about. So the syntax czar was responsible for causing a decision to happen. Has anybody got another question? One more? I think we've got time for one more. Is that where I'm looking at Andre now? Yes. Go. Thank you.
So I've been doing this for a long time as well. And I remember going to a summer school in 1981, and I was very inspired by David Turner and other people who claimed that the software crisis was the big problem we were facing, and we needed an order of magnitude improvement in programmer productivity. Remember that? And functional programming was going to make us 10 times as productive. I think if you compare with languages like Pascal and C and Fortran, that one should do, that has certainly been delivered. But where will the next order of magnitude come from?
Oh, where does the next order of magnitude, this is John Hughes, by the way, in case you didn't see on the video, where does the next order of magnitude in programming productivity come from? A good open-ended question to finish on. Either of you. I'm off the hook here.
Maybe in 10 years, artificial intelligence will do for programming what it's now doing for photographic processing.
Yeah. I think program synthesis.
Yes, it will synthesize programs that will be a little bit bizarre in some of their corners, but mostly get the job done.
Yeah, I'm not sure I believe in AI as a program synthesis tool, except for big programs. Anyway, John, do you have an answer yourself, by the way?
I would say, I would hope.
Use the microphone so that they can hear you.
I would put my hope in program synthesis also, but it's quite a tall order. I mean, it means that you have to specify what you want, an order of magnitude more compactly than we do today. And that sounds quite difficult. But if anything can do it, maybe program synthesis can.
Good. Okay, I think I can see Andre looking at me in a significant kind of way. And it's 6 o'clock. Well, I promised we promised that we finished at 6. So, Arvind and Guy, it's been a privilege for us to have enjoyed this conversation with you. Thank you so much for what you've done for all of us. Your scholarship, your leadership, your engineering skill, and actually your personal friendship and support for many of us. Thank you so much. We salute you.
Thank you for the opportunity.